Hi, welcome to Lecture 9 of CS294-158, Deep Unsupervised Learning, Spring 2020. I hope everyone had a good spring break despite the rather unusual circumstances. Today, we will be covering two main topics, semi-supervised learning and unsupervised distribution alignment. Before diving into that, a couple of logistics. So, COVID situation and a quick mid-semester update. Well, first, we hope everyone and their families are able to keep healthy during these pretty unusual times. Please prioritize your health and well-being. And accordingly, please don't hesitate to let us know if this class would interfere with that, and we'll be happy to figure something out on a case-by-case basis. Since we are just past the middle of the semester, and since there's some replanning per the current situation, here's a quick overview of what's still ahead in this class. Today, we have Lecture 9, which will cover semi-supervised learning and unsupervised distribution alignment. Next week, we'll have Lecture 10 on compression, which will be a live Zoom lecture. Then at the end of next week, your final project 3-page milestone reports are due. This is not graded, but it's a great way to get feedback and make sure you're on track for a good final project. We'll try to give you feedback into your Google Doc that you share with us on pretty short turnaround. Then we'll have Lecture 11 on language models with a guest instructor, Alec Radford from OpenAI. Then we'll have our midterm, which will adjust to the current circumstances. We'll see how we do it, but the high-level model will probably stay similar, that we want to cover the main derivations that we've seen in this semester and have you be able to rederive those. Then we'll have our final regular lecture, Lecture 12, on representation learning and reinforcement learning. That'll also be a live Zoom lecture and recorded. Then is our R week, which hopefully gives you time to catch up on a lot of things, and hopefully including on making extra push on the final project for this class. And then during finals week, on the 13th, the Wednesday, there's final project presentations. We'll see how we do that with the new situation, and final project reports will be due at that time also. With all the logistics covered, let's dive into the technical content for today. So we'll cover first semi-supervised learning, which Aravind will cover, and then we'll cover unsupervised distribution alignment, which will be covered by Pieter Chen. And actually, we'll use the lecture he gave last year also for this year.
Welcome to Lecture 9A of Deep Unsupervised Learning. In this part of the lecture, we'll be covering semi-supervised learning. So first, to understand what is semi-supervised learning, let's look at supervised learning. In supervised learning, you have a joint distribution of data points and labels, and you sample from that joint distribution. In expectation over the samples from the joint distribution, your goal is to maximize the log probability of your classifier, log p of y given x. We all know how to do this as far as procedurally how it's done. You basically sample image, label, or like sequence and particular label, or any pair of x and y from your data set, assuming they're all independent and identically distributed. And you don't know what the analytical form of the distribution is, but you assume that it is some complicated distribution. And you just keep sampling multiple points repeatedly and perform stochastic gradient descent to optimize this objective. Now, what is semi-supervised learning? Assume that you have an unlabeled data set, du, where x is sampled from p of x, which is the marginal corresponding to the joint distribution from which the labeled data set is sampled from. So you have du, the unlabeled data set, and ds, the labeled data set. And your goal is to perform the same thing earlier, which is supervised learning on the labeled data set, but with access to this extra unlabeled data that's coming from the same marginal. So that's the assumption we make in semi-supervised learning, which is that the unlabeled data is coming from the marginal that correspond to the same joint distribution that the supervised data is coming from. And that's just a mathematical assumption. In practice, you can't really ensure that, but your goal is to make sure that you can use this extra unlabeled data to perform your supervised learning objective even better on the labeled data. So not mathematically, here's a summary of what we just described. Take a task like classification, a fully supervised scenarios where you have every single data point given to you in the form of image, label. You're trying to predict the label for new images. That's your task for supervised learning. Now, the scenario is you're going to be given a few unlabeled samples, but you're going to be given a few labeled samples, but you're also going to be given a lot of unlabeled samples. Now, labeling is a time-consuming process and potentially very expensive and actually pretty hard in certain domains like medicine, right? So, or detecting rare events in self-driving for that matter. So if you have a lot of unlabeled data and your training data set can be reparameterized now as having some pairs of label data points, image, label, and also a lot of other data points where you just have the image. And your goal is take this extra data points where you don't have the labels and try to improve a classifier that just works with the label data. And how you do it is totally up to you, and that basically decides what kind of semi-supervised algorithm you're gonna come up with or use. And we're gonna look at, in this lecture, we're gonna look at how various algorithms can be designed, what are the mathematical or intuitive aspects of these algorithms, and how they compare to each other, and how they can scale to larger data sets like ImageNet and beyond. So as to why we even interested in this problem, semi-supervised learning is pretty important because label data is, even though you can collect label data very easily these days with a lot of data annotation startups, it's still expensive in terms of hiring people to write annotation manuals for actual data annotators and preparing graphical user interfaces so that all this is done really fast, and making sure it's stored on the cloud efficiently and syncing from the browser to the cloud. There are lots of engineering challenges involved in setting up a good data annotating tool. Now, that's not to say we are never going to do it. We are still going to do it, but the goal is to make sure that we don't do it as much as we are doing it right now, because we also have access to a pool of unlabeled data that we can potentially exploit and maybe even improve the performance of labeled data systems. This is similar in spirit to our goals for self-supervised learning, and semi-supervised learning is a different take on this. Self-supervised learning can work with just unlabeled data, whereas semi-supervised learning needs some labeled data and a lot of unlabeled data. That's the key difference. So here is a slide from Tang Wang, who took this particular picture from Vincent van Hoek on a blog post called The Quiet Semi-Supervised Learning Revolution, where the belief of many ML practitioners, at least until recently, was that semi-supervised learning will be really useful in a low data regime, where it's really, really going to be better than normal supervised learning when you hardly have any label data. However, once you collect sufficient amount of labels, supervised learning will catch up and eventually be much better. This is why a lot of startups don't care about semi-supervised learning, because the amount of effort needed to do research and engineering to get a semi-supervised learning working, especially given that it's a very new field, is a lot more than the amount of effort needed to collect the extra data points, and you're guaranteed a better performance anyway. So that's the rationale so as far as the left plot goes. But look at the plot on the right. The dream of many semi-supervised learning researchers is that it not only is going to be super useful in the low data regime, but it's going to be extremely useful even in the high data regime, because it's still going to give you that final few percentage extra performance because of access to a lot of unlabeled data and learning much richer or more fine-grained detailed classifiers because of that. And that's basically what's happened recently. And we look at the history of the field in recent times. So the core concepts needed to understand semi-supervised learning are very few, and we're just going to look at them at a very high level. And it's really, really intuitive and not hard to understand. So the first principle we look at is confidence of classifiers versus minimal entropy on unlabeled data. It's a very nice coupling that this principle shows and is being used to very good effect in recent work. And mathematically, there have been papers on these two ideas, which is first idea is entropy minimization, which we look at, which is the idea of taking unlabeled data and making sure that the classifier training on labeled data has minimal entropy on unlabeled data. So that way you're making sure that the classifier is confident even on unlabeled data. It's a useful way to regularize your classifier. The second idea is pseudo-labeling, where you take your classifier, you ask the classifier to predict what the labels are for unlabeled data, and you take the confident predictions and convert them to extra data as if it was the ground truth and train the model on those data points. So this idea is also referred to in literature as self-training, which is the idea of training the model on its own predictions if the model is confident enough, and expanding your data set and regularizing your model further. This is a little tricky because it has this reinforcing effect of the model using its own predictions, so it needs to be done very carefully. So that's the caveat there. And the other way to add noise to a model to regularize the model is virtual adversarial training, which we really look at in detail. But the idea is similar to how adversarial training is performed for adversarial examples and images where you have a particular label and which you're trying to fool a classifier into believing that this image corresponds to that label, and you're trying to add a particular noise in the direction of the gradient of the output with respect to the input, such that the model starts producing some other label. Similarly here, you want to make sure that the model, the semi-supervised learning model, is regularized in the directions around which the on unlabeled data, you want to find directions in which the classifier is likely to be confused, and you want to make sure that the model is not confused in those directions. So that's the idea in virtual adversarial training. And there are also ideas like label consistency, which is make sure that the augmentations of the sample have the same class. So you have an image. We know that we use a lot of data augmentation in regular supervised learning. But in semi-supervised learning, you have a lot of unlabeled data. And you can't apply data augmentation to them if you're not passing them to the classifier. But instead, what you can do is you take an unlabeled sample, you create two different augmentations of it, and you tell the classifier that its predictions on these two different augmentations of the unlabeled data should be roughly similar. Because even though you don't have the label, you tell the classifier that whatever it's predicting, it should be similar. And this way, the classifier gets a lot of structure and loss function and parameters that are being learned from unlabeled data. A lot of constraints are being imposed. And therefore, it's going to be much more regularized than just training on the labeled data. So this is a very neat idea, and it's also similar in spirit to things you've seen in self-supervised learning, which is the idea of taking two different views of an image and trying to make sure that they attract each other relative to another image. So it's basically consistency constraints embedded into your encoder. And various different ideas in the past have attempted to do this, and we are going to look at them, like the pi model, temporal ensembling, and mean teacher. Finally, we're going to look at regularization, which is the idea of taking a model and making sure that it's generalizing well to a new unlabeled data set or new validation set. So typically people use weight decay, dropout, data augmentation, for making sure that the classifier is generalized well. And those are also pretty important in semi-supervised learning. And methods that I've attempted to use these are unsupervised data augmentation, or UDA, and MixMatch, which we'll look at in detail, but there are also other papers that we can't really cover in the scope of this lecture, but you should check out other papers that are related, that I mentioned as related work in these papers. Finally, we look at the idea of co-training or self-training or pseudo-labeling. All these are ideas that have already been mentioned in this list of bullet points, but there is a particular paper, Noisy Student, which has taken these ideas to a whole new level in terms of performance. And so we'll look at that in a little more detail. So entropy minimization. It's a very simple idea. You have a lot of unlabeled data, and you have your labeled data, and you're training a classifier on the labeled data. But you want to make sure that the unlabeled data is also influencing the classifier in some way. So one simple idea is you take your classifier and ask it to predict on the unlabeled data. And you want to make sure that the classifier is pretty confident on the unlabeled data, or rather its entropy of the class probabilities it outputs on the unlabeled data is small enough. And this way you ensure that the structures, this way you ensure that the classifier is understanding the structure of the unlabeled data by trying to be confident about it. So it's trying to find a solution for the labeled data in such a manner that it will be pretty confident on the unlabeled data as well. So this is one way to do semi-supervised learning. It's a very old idea. And pseudo-label is a very similar idea, and we'll see how it's actually similar. But the goal here is to take your classifier that's being trained on labeled data and ask it to predict on unlabeled data. And you pick the most confident predictions and you turn them into extra labeled data as if that were the ground truth. And you train the classifier on its own predictions. So the classifier is making a bunch of predictions, and those are being converted to ground truth, proxy ground truth data for itself. And it's just going to train again on new data sets created from the unlabeled data based on itself. And this principle is also referred to as self-training. And there is a connection to entropy minimization. So here's the connection. So consider an image X and classes Y1, Y2, Y3. And let's say you're doing a classification problem. And let's say there's a classifier A with probabilities for the output classes being 0.1, 0.8, 0.1, and a classifier B with the probabilities being 0.1, 0.6, and 0.3. So classifier A clearly has lower entropy, and you can say it's more confident. It's more confident that the true ground truth is Y2, and its score for Y2 is much higher, and the scores for the other two classes are more similar and lower compared to class B. So there is clearly a connection to be made in terms of a classifier being more confident and therefore having lower entropy in the output probability distribution of the classes, and therefore minimizing the entropy of your classifier on unlabeled data is akin to taking your classifier's outputs on unlabeled data. If they're confident enough, you're trying to train on its own predictions. So it has a similar effect, and mathematically it's shown in these older papers that have been linked here. So you can go and check it out. And the next thing we're going to see is data augmentation for label consistency. So you take an image, let's say it's whether it's unlabeled or labeled, you're given an image, and now you create two different augmentations of it. So similar, this is the same picture we used in SimClear and Moco. So I'm just using it so that you kind of relate this concept to the earlier lecture where we talked in self-supervised learning about data augmentation consistency using contrastal losses. So similar ideas are being used in semi-supervised learning as well. So like I said, you're already using data augmentation for labeled data, so it doesn't matter if you enforce consistencies there. But for unlabeled data, if you take two different views and make sure that the logits are close enough of the classifier that's being trained on labeled data, that enforces a lot of structure on the labeled data. So you just make sure that the predictions are roughly similar. And if you do this for a lot of unlabeled data with a lot of different data augmentations, then your classifier is getting very much regularized and generalizable, even though it's training on very little data. So that's the idea of label consistency constraints using data augmentation. And the more data augmentation you use, the better it is. So that's it for the foundational material. Next, we'll actually look at different semi-supervised learning algorithms, like the pi model, temporal ensembling, and virtual adversarial training, and so on. But we'll also look at how the algorithms compare to each other. And this particular paper from GoCoBrain, Realistic Evaluation of These Semi-Supervised Learning Algorithms, compares these various different semi-supervised learning techniques on the CFAR10 and SVHN dataset, which are reasonably small, and you can run a lot of prototyping experiments on that. So the four algorithms we're going to be looking at are pi model, temporal ensembling, main teacher, and virtual adversarial training. So basically, let's look at the pi model. Basically, the idea is pretty much whatever we talked about label consistency. You take your image, you create two different views using a stochastic data augmenter. By stochastic, it could be like a random crop or a sequence of data augmentations whose sequence is randomized, or whether you apply random grayscale, so on. And now you take you pass it to the model, and the model itself could be stochastic. It could have dropout. So every forward pass could give you a different output even for the same image. And you get two different latent variables for these different randomizations, both in the input and in the model. So every time you make a forward pass, for label data, you can enforce the regular supervised cross entropy loss. And if you throw unlabeled data, you can enforce the square difference between the outputs of the model for two different views. And for label data, you can enforce both of these losses, while for unlabeled data, you just enforce this label consistency loss, which is you just take your output before the softmax or even after the softmax. It depends on how you want to implement it. But you take a particular layer at the end and you make sure that the layers are similar for two different views. And you weigh both these losses together. So one is going to be the unsupervised or semi-supervised loss, and the other is supervised loss. And you can actually control which loss actually dominates the training in the beginning and the end. So for instance, one reasonable motivation is you can make sure that the supervised loss dominates in the beginning so that the model already learns how to classify images. And then you can ramp up the weight for the semi-supervised or unsupervised loss so that it's learning to structure the unlabeled data in similar fashion. So this idea is called pi model. And this is the serial code for pi model. Xi is your training, Y is your labels, WFT is your ramped up weight for your unsupervised function, and F theta of X is your neural net that's doing the classification task, and it could have some dropout, and therefore it could be stochastic. And G of X is your data augmentation, which is also stochastic. And you basically perform two different augmentations of your minibatch, get two different outputs, Zi and Zi tilde, and you make sure that Zi and Zi tilde are close to each other using a square error loss or some distance metric. And you also make sure that the predictions of the classifier are matching the true ground truth whenever you have the labels. So that's really it. That's as simple as it can get. The pi model, basically it's using the label consistency principle. So temporal augmentation does something slightly different, which is it says, hey, I don't want to do forward passes of two different views all the time because it's expensive. Why not? Let me just keep a moving average of these sample embeddings for every single sample and make sure that the consistency is enforced across time. So I would still do a stochastic data augmentation, stochastic network. I would get an embedding every time in the forward pass, but I would say that those embeddings should be close to some historical version of the same samples embedding in the past. And so that way, you're still enforcing some kind of data augmentation constraints because you would have done a different augmentation in the past, but you're going to keep an estimate of it for every single sample separately. So this is very similar to those ideas we've talked about in the GAN lectures earlier, improved GAN, where there was a constraint on the parameters to be close to the historical versions. So this is done at a sample level. And other than that, it's pretty much the same as the pi model. There's a cross entropy loss, there's a ramped up function for the unsupervised objective, and both the objectives are jointly optimized together. So this is the pseudocode for temporal ensembling, is proposed in the same paper where pi model is proposed. So one negative thing about temporal ensembling is it's not going to scale with the size of the data set. You're not going to be able to maintain a separate moving average embedding for every sample if your data set is so big enough, like a million or billion images. So Mean Teacher basically amortized that and said that, hey, if you want to keep an exponential moving average of your embeddings, why not just keep an exponential moving average of your parameters so that you still take two different views, but make sure that the embeddings match that of the moving average versions rather than creating separate moving average embeddings for every sample. So you take your model theta, there's also the EMA version of theta, and you make sure that the embeddings that you get for one view matches the embeddings that you get for the other view, but with different encoders, basically. So that's the idea of this mean teacher approach, where the teacher can be considered as the EMA version, and that you think about it as a teacher because it's giving you these constraints. And you also perform the classification task, classification loss in parallel simultaneously. Finally, let's look at virtual adversarial training. So in adversarial training, you're using this fast sign gradient method where you basically calculate the gradient of your input image, basically calculate the gradient of your output with respect to your input image, which is a huge dimensional vector or matrix, depending on what your input is. And you move your input in the direction where you basically get this gradient, you get this sign, and you move your input in a small epsilon in that direction. And that lets you fool your classifier. And you want to make sure that your classifier is not full if you're for these perturbations. And so you would perform adversarial training to make sure that the classifier is not fooled at these data in these different perturbation directions. Now in semi-supervised learning, you don't have the labels for unlabeled data. So how would you do adversarial training there? So the idea is to do virtual adversarial training where you look at the distribution of your classes instead of a particular class, because you don't want to take a particular class and see the perturbation direction for that class. You take the distribution of classes and you take some kind of distance metric between your unperturbed data point and your perturbed data point. You're trying to figure out a direction that maximizes the scale. And it turns out if you linearize the scale term, you can actually solve for this direction R using power iteration. And once you get the direction, you can make sure that you enforce structure in your classifier around unlabeled data by trying to make sure that on these perturbations on unlabeled data, the classifier is still not fooled, even though you don't have access to the true label. So that's why it's referred to as virtual adversarial training. It's not actually adversarial training, but it shares its principles with adversarial training done cleverly with some mathematical tricks. And this is basically the pseudocode for the power iteration method, which I mentioned, because it works because you linearize the KL term. So that's it for the techniques: pi model, temporal ensembling, mean teacher, and virtual adversarial training of that. These are the 4 techniques considered in this comparison paper, and they make sure that they use the same architecture for all these techniques because prior work did not do that. So they use a wide ResNet, and the idea in a wide ResNet is your normal ResNet goes through a bottleneck, and the wide ResNet doesn't do that. It just uses 3x3 cons and does no 1x1 con for downsampling. It's as wide as possible. So given all these constraints, given all these similar architectures, similar hyperparameters for various different semi-supervised learning algorithms, it turns out that virtual adversarial training performs the best. If you look at C410, which is 4,000 labels, so C410 originally has 50,000 images, so you basically just use 46,000 unlabeled data points and 4,000 labeled data points, which is like 400 labels per class. So that's really tiny compared to what the original data set is. And virtual adversarial training gets an error rate of 13.86%, which is the best among all the other methods. And virtual adversarial training plus entropy minimization together gets even lower error rate of 13.13%. And the trends are similar for the SVHN dataset, where virtual adversarial training plus entropy minimization outperforms all the other methods. And the authors also say that they report much better baselines than prior work. Like for instance, in prior work, the baselines reported had much higher error rates than what the authors report. So this paper actually took the effort to make sure that all the ablations are done carefully. And one negative thing about semi-supervised learning on CFAR is that if you use something like a pre-trained ImageNet, you take an ImageNet that was pre-trained on ImageNet labels, and then you fine-tune it on CFAR, you actually get better numbers than using the unlabeled data on CFAR itself. Even though CFAR, unlabeled data on CFAR is coming from the same underlying distribution, and ImageNet is a completely different distribution with completely different image sizes. So that's slightly bad. So, and there is a significant difference, as at least 1.1 plus percentage difference. And even if you address the class overlaps and remove the classes that are overlapping with CFAR, it's still, you still get a lower error rate than just using semi-supervised learning on CFAR. And the authors also analyze things like, hey, if your unlabeled data has, so in CFAR there are like around 10 classes, and if you assume that the unlabeled data doesn't have the uniform class distribution as labeled data, and you can play around with what the distribution of unlabeled data points are as far as a class overlap with labeled data is, it is clear that as the distribution mismatch increases, virtual adversarial training is the most resistant compared to all the other approaches. Similarly, if you vary the number of labeled data points, obviously the test error is going to be lower as the number of labeled data points increases, because that's slowly getting into the supervised learning regime, and all the methods roughly perform similar. But in the extreme scenario where you have very few labels, 250 labeled data points and so on, virtual adversarial training is significantly the best in SVHN, and it is still the best on CFAR, though its other methods are competitive as well. So the lessons from this paper are, when you compare different algorithms in semi-supervised learning, you should make sure that you use a standard architecture and equal training budget, which is you should spend equal amount of time tuning hyperparameters for all of them. And if your unlabeled data is coming from a distribution that doesn't necessarily overlap with your labeled data points, then the benefits of semi-supervised learning will not be there. Thirdly, most methods that like don't work well in a very, very low data regime. So this is not true right now, but this was true when that paper was published. And we'll see how it changed over time. And transferring pre-trained ImageNet produced better error rates, but again, it's not true right now. So this is an old paper, but the main reason for going through that is to introduce all these different techniques like the pi model and virtual adversarial training and temporal ensembling in the main teacher. So the agenda for the rest of the lecture is to cover 3 very recent papers on semi-supervised learning that actually have taken semi-supervised learning to a whole new level unsupervised data augmentation, MixMatch, and noisy student. So before that, let's actually take a break. Okay, we're resuming. So first, let's look into unsupervised data augmentation for consistency training in semi-supervised learning. So this is a paper from Google Brain from Kwok Lei's group, and these slides are from Tang Luang, who's one of the authors in this paper. So we've already seen how important data augmentation is, and it's been significantly useful in supervised learning in the high data regime. But if you just do supervised learning, if you don't have a lot of labels, just data augmentation isn't going to get you very far. Even if you use extremely aggressive data augmentation like auto augment, which is shown here, where you basically can rotate, shear, and add colors to some scene and create a lot of different views of the same image. Similarly, in language, you can create different versions of the same phrase or sentence using the technique called back translation. So what it does is basically take a sentence in a particular language, translate it into another language, and then translate it back from the other language to the existing first source language. So you go from a source language, you go to a target language, and you come back from the target language to the source language. So you hope that this entropy in the decoder and the encoder will result in a new version of the same sentence. And examples are here. So the source sentence here is, given the low budget and production limitations, the movie is very good. And if you look at the 3 different back translations, since it was highly limited in terms of the budget and the production restrictions, the film was cheerful. There are a few budget items and production limitations to make this film a really good one. Due to the small dollar amount and the production limitations, the else film is very beautiful. So the first and third versions are particularly really good. Well, the second conveys a slightly different meaning, but it's more or less there. So this is giving a lot of diversity, and based on which language you move to, you're going to get very different outputs. And also the same language, you're going to get different outputs for different decoding. So the key idea in UDA, or unsupervised data augmentation, is apply the state-of-the-art data augmentation techniques on unlabeled data for consistency training and semi-supervised learning. You've already seen that Pi model, or so Pi model was basically doing consistency training, but it was a pretty old paper, and data augmentation as well as neural architectures were not as developed back then. So you can think of UDA as doing Pi model right by using a lot of data augmentations and the right architectures. So here's a nice way to understand UDA. So think about label data, and you have X and you're ground truth Y star, and you're training a classifier P theta Y given X. And you have your standard supervised cross entropy loss that makes sure that the logits of the true class are really maximized. And you also have unlabeled data. So this is the situation in semi-supervised learning. And models like virtual adversarial training add noise to regularize the model's predictions. And the noise is basically in the virtual adversarial training direction where you calculate the gradient in an approximate fashion. And next, you have this thing called unsupervised consistency loss, which is you take the noise version of the model and your original model, and you make sure that the logits are roughly similar on unlabeled data. So this is something you already know. And the final loss is a combination of supervised and unsupervised consistency loss. And you can see that virtual adversarial training actually works pretty well. So this is a very nice illustration of virtual adversarial training, even though it's being presented in the UDA slides. So the uncolored data points are unlabeled data, while the green and pink data points are the labeled data. You only have roughly 8 data points which are labeled. But after performing virtual adversarial training, after enforcing the consistency between the model and the noise version of the model, where the noise comes from that, you can see how those labels propagated and covered up the spiral. So that's really cool. So that's the goal of semi-supervised learning, to do this really well in high dimensions when you have a lot of data and a lot more parameters. So you can think of UDA as creating this noise at the input level using various different data augmentations. And depending on the modality, for instance, you would use auto augment for images, you would use DFID word replacement or back translation for NLP. And based on that, you create different augmentations of the same image or same sample, and you enforce this consistency loss in the unsupervised consistency loss part. And you also do supervised cross entropy loss, and you together optimize this. So that's basically UDA. And augmentations provides a diverse and valid perturbations for your input. So like I said, back translation produce 3 different versions that look very different from each other and convey roughly the same meaning as the original source sentence. So in this case, they actually went from English to French and back to English, but you could also think of doing it to other languages. And you can increase the diversity by playing around with the temperature, various different sampling techniques like beam search and nucleus sampling. And you know, whenever you decode, you use a softmax, so you can always, if you use a temperature there, you're going to get diverse samples if you use high enough temperature, and if you use a low enough temperature, you're going to get the most confident samples with less diversity but high quality. So you can control for that. Similarly, in images, you can use auto augment, but depending on the type of augmentation, you can control the strength of the augmentation and get sufficient distortions based on what level of distortion you care about. So let's look at the experiments carried out in this paper. So in language, they experimented with document classification or sentiment classification or review sentiment analysis. So if you look at the size of the data sets, they have like 25,000 or 560,000, 650,000 samples and so on. And the error rates before BERT and after BERT are mentioned in the different lines, and you can see how BERT has significantly improved the error rates. So what they did in the UDA paper is, for various different initializations, random, BERT-based, BERT-large, and BERT fine-tuned, they have numbers for whether you use UDA or whether you don't use UDA, but you notice how the number of label data points have changed by orders of magnitude 3 or 4 higher. So if you look at IMDb, you earlier had 25,000 label data points, but the authors run this experiment with 20 label data points, which is 3 orders of magnitude lower. Similarly for Yelp, it's 2.5K versus 650K, and so on. And you can see how the performance, especially when you use BERT fine-tune, is on par with the BERT large that's trained on all of the label data points. So the performance you get from taking BERT large and fine-tuning on the fully supervised baseline is actually on par with what you get from UDA plus using BERT fine-tune, but just on like 1000x fewer labels, which is incredible. So it means that the consistency losses using back translation is actually working really well. Secondly, they have this idea called training signal annealing, which is you want to prevent overtraining on the label data. So you have very little label data, so you don't want to make sure that you want to make sure that your classifier doesn't overtrain on it. And for that, they actually have something like a thresholding procedure where they take the classifier, and if it's sufficiently confident, they don't train the classifier on those points. And this threshold is actually varied over time. So you have an indicator variable of whether the classifier's output logic score is less than a threshold. And only if it is, you're going to have the model train on those data points, or else you're just not going to backprop those gradients. And this threshold has you could play around with different schedules. You could be really confident at the beginning, At the end, you want to make sure that the thresholds are actually high enough so that the model is not training again. In the beginning, you don't want to have a high enough threshold, right? So because your model could be erroneous. So they play around with linear, exponential, and log and in the paper. Finally, this is a really cool plot that shows the dream of semi-supervised learning, which is the benefits hold even in the high data regime. Even when you have 25,000 label examples, the performance that you get is from semi-supervised learning is better than supervised BERT fine-tune. So it's actually able to take advantage of all the unlabeled data you have. So next, let's look at the computer vision experiments carried out in the UDA paper. So basically, they use the standard benchmarks on CFAR10 and SVHN semi-supervised learning, which you saw in the prior work on realistic evaluation of semi-supervised learning algorithms. So a lot of these baselines are from that paper where they use a wide ResNet with 28 layers. And you can see how the parameters are controlled for all the different algorithms. And the numbers are reported for CFAR with 4,000 labels and SVHN with 1,000 labels. And UDA is actually the best algorithm in this setting with an error rate as low as 5% on CFAR and 2.5% on SVHN. And with architectural changes like shake and shake drop and pyramid net, they get all the way down to 2.7%, which is significantly lower. So just 4,000 samples, they're as good as 97%. They're better than 97% accurate on CFAR, which is the kind of accuracies you usually get with using all the label data points. So that really means the domain consistency, the data augmentation label consistency is really, really helping them. And the model is also scaling well with larger networks. So when you move away from 1.5 million parameters that was typically used in semi-supervised learning for CFAR earlier to a model that's big enough that has 26 million parameters, the error rates are getting significantly lower. So this shows that this technique scales well with the number of parameters you use. Next is how you can actually match the complete supervised baselines with just using order of magnitude fewer table data points. So the complete supervised baseline uses 50,000 labels, and this one uses 4,000 labels. So that's 10x or like more than 10x fewer. And if you look at the numbers, you basically get 5.4% error rate with supervised and 5.3% with UDA for the wide ResNet 28 architecture. And for the other models, even though UDA is slightly higher for shake, for shake drop, it actually matches the supervised baselines. Though it's not as good as the auto augmented version, it's still very, very close. Finally, they also ablated for how much data augmentation matters, and it seems to matter really. It's really the biggest deal, as we would expect, because we've seen that in self-supervised learning as well, and that's what they observe even here. So the summary of UDA is that it's a data augmentation technique that's applied on unlabeled data to improve the performance of a classifier that's trained on very few labeled data points. And data augmentation is therefore a critical part of this pipeline, and it's an effective perturbation technique for semi-supervised learning. So it's even more effective than perturbing the model. And UDA significantly improves for both language and vision by 10x or 100x or 1000x fewer label data requirements, and it combines very well with transfer learning like BERT and scales well with model parameters and model sizes. So they also experimented with ImageNet, where they take unlabeled ImageNet of 1 million examples and 1 million unlabeled data points. And they use 10% label data, which is 100,000 labels or 100 labels per image. And pure supervised gets 55%, whereas their model UDA gets 68 close to 69% accuracy, which is at least 13% better. And this shows the benefits of using more unlabeled data points. So Another thing that they tried is having a data set that's even larger than ImageNet, which is the JFT data set from Google. It's an internal data set that's on the scale of Google Photos. And they use 1.3 million images from JFT to just to see how much the domain mismatch works out. And obtaining extra in-domain unlabeled data, actually the out-of-domain unlabeled data hurts their performance. And so you can see that it's not actually working as well. So using a more filtered data set actually works better for them. And they also have ablations on different the schedules for the thresholding, and they find out the exponential schedule works better for language, but linear schedule works better for images. So that's something very empirical. Diversity constraints. How do you control the diversity constraints for making sure that you have effective data augmentation? They use a lot of hacks like minimizing the entropy when you're decoding, using the softmax temperature controlling, and confidence-based masking for your ImageNet case, where they found the auto distribution data set unlabeled data set like JFT to hurt the performance, and therefore they would take the most confident predictions from your label data and use that to filter the unlabeled data, and then they would find gains. So domain relevance-based data filtering is like a critical aspect of using unlabeled data for improving the performance of labeled data in semi-supervised learning. We already saw most of the mathematical or intuitive foundations of semi-supervised learning make the assumption that the unlabeled data is coming from the same data distribution as the marginal corresponding to the joint distribution that you use for labeled data points. But that's often not the case in practical scenarios, because the data set of unlabeled data is usually something coming from some other data set or some other data source, and you want to make sure you still transfer knowledge, and therefore that's a restrictive assumption to make. But in practice, it can be, there's a workaround using various kinds of filtering techniques that this paper proposes. So next, let's look at MixMatch, which is another very interesting, a similar paper in similar spirits. So the key idea in MixMatch is you take unlabeled data, you perform a lot of different augmentations. And now you run all of these different augmentations to the same classifier, and you get the predictions. And you average the predictions across these augmentations, and you would end up with a bunch of class probabilities. You can sharpen those class probabilities with softmax temperature controllers. And once you get a sharpened distribution, you have an idea of what the classifier would have guessed for the unlabeled data point. And now what you're going to do is you're going to take this and use it as part of your label data for every label data update in your semi-supervised learning. So it's that simple. Only thing is you're making sure that your guess for unlabeled data comes from averaging over multiple augmentations and sharpening the distribution so that it's confident enough. So it's called MixMatch because it uses the mix-up trick. Firstly, if you're not familiar with mix-up, the idea is you take your input X and your output Y, and let's say you're training a model to predict Y from X. You basically create convex combinations of two pairs of X1, Y1 and X2, Y2 and create a new data point. So for images, it would be something like, for every pixel, you take the weighted combination of the pixel from the first image and the pixel from the second image, and you would just average those two pixels and create a new image. And similarly, you would average the corresponding ground truth labels and create a target ground truth for your cross entropy with logits loss. And this technique is called mix-up, and it's a data augmentation technique. So MixMatch basically does the following. It takes a batch of label data and a batch of unlabeled data and produces a new batch of processed label examples with this guessing technique and mixing up. So let's look at the English part of this pseudocode. Apply data augmentation to XB. So basically you have a batch of label data points X, XB, PB, and unlabeled data points UB. So you apply the data augmentation to XB, and you apply Kth round of data augmentation to UB, which is the unlabeled data point, and you compute the average predictions across all the augmentations of UB. In practice, they just use K equal to 2, but K can be really large if you want it to be. And you apply temperature sharpening, which is softmax temperature, to make sure that the average predictions are peaky enough. And after the peaks are obtained, you can take the argmax and get the corresponding classifier, corresponding data point for proxy data point for the classifier. So you augment the labeled examples with these guess labels, and using these guesses and the original labels, you create an augmented mini batch. And you shuffle or combine these mini batch data points using the mix-up trick. And once you apply mix-up to the labeled and unlabeled data, you can just train a regular semi-supervised learning model that has domain consistency losses and the supervised cross-entropy loss, treating this new batch as this mixed match. So mixed match is producing this processed labeled plus unlabeled data batch from 2 different data batches that are coming independently. So the loss function for mixed match is going to be the regular cross entropy loss for your classifier plus some kind of consistency loss for your unlabeled data points that you normally use in semi-supervised learning with some weighting constant. And in practice, it works really well. Earlier, you saw in the realistic evaluation of semi-supervised learning algorithms that all these techniques were not really working well. And this was concurrent work with UDA. And you can clearly see how it's really improved the performance on CFAR10 and SVHN. So here are the numbers. You can see that it's not only working in the regime where you have 4,000 labeled examples, but it works all the way well. Even when you have 250 labels, MixMatch is able to get all the way down to 10% error rate on CFAR, which is very impressive. So 250 images per class just means 250 images of labels just means 25 images per class, and you're still able to get a classifier that gets around 90% accuracy. So that's it for MixMatch. MixMatch and UDA were like concurrent work and had very similar ideas, different kind of implementations. And UDA is probably more broader in terms of applications to NLP as well. MixMatch is well analyzed and thoroughly ablated for CFAR and SVHN. So let's look at the final paper in this agenda, sub-training with noisy student. This is the largest scale semi-supervised learning experiment conducted in machine learning so far. These are also slides from Tanggu Wang, who's one of the authors in this paper. So as I said, there's the semi-supervised learning had a background, which is the dream is to make sure that unlabeled data improves the performance of supervised learning on labeled data, even when you have a lot of labels. And that's what this paper tries to achieve. So you already remember how unfiltered JFT was not able to give sufficient gain on ImageNet for the UDA paper, and they actually use clever filtering techniques. Noisy Student is actually a larger scale version of that. So the way it works is as follows. You train a teacher model with a lot of label data, train a really, really good classifier, and ask the classifier to predict on unlabeled data. And you infer the pseudo labels on unlabeled data, and you train a student model with the combined data of the teacher of the original label data that you use for the teacher, as well as the guess labels on unlabeled data. And you add noise to this process through data augmentation, dropout, and stochastic depth, which is another version of skip connections with stochasticity, and create a noisy student. That's why it's called noisy student. You're going to add a lot of data augmentation to this process. And once you do that, your student model is pretty good. It's highly regularized and also trained on a lot more data. And therefore it can't overtrain on anything, but still it trains on a lot of different proxy data you generated from unlabeled data, and which has already been filtered because it's only taking the confident predictions. So now you can treat that student as a new teacher and repeat this process multiple times. So you take the new student as a teacher, you basically train it on label data. You infer the pseudo labels on label data again with this new teacher, and you create a new student and so on, and repeat this process like multiple times, and you get a really good classifier at the end. So here are the experiment settings. The architecture they use is EfficientNet, and the model noise that they use is dropout and stochastic depth. The input noise they use is Randog, which is a version of AutoAug that's more efficient. And for pseudo labels, they use the soft pseudo labels, the continuous values. They don't actually use the one-hot encodings. And the label dataset they use is ImageNet, which is 1.3 million images. And the unlabeled dataset they use is JFT, which is 300 million images. And they basically do iterative training where they take the biggest EfficientNet model possible and actually make it wider for the next scenarios. So the original teacher could be B7, which is the widest and deepest EfficientNet that exists. And the student model that trains next could be another bigger version of that model, which is the L2 model that they call. So in terms of results, they actually have the state-of-the-art numbers for ImageNet, where they get to 88.4% top one accuracy, which is significantly better than any other model. And the previous best was 86.4%, which are actually trained on 3.5 billion labeled images from Instagram. So with just 1.3 million labeled images and 300 million unlabeled images, they're actually able to surpass those numbers by 2%, which is significant, especially in those regimes. And they do that with 1 order of magnitude fewer labels, and they actually do that with twice as not smaller in terms of number of parameters, because they use EfficientNets, which are much more efficient in terms of parameters and flops than ResNet or ResNext. So the improvements also exist without iterative training. So it's not that they actually need iterative training. So even without iterative training, they get significant improvement. With just one iteration, they can get a minimum of 1% improvement for all the different model regimes, be it B0, B2, B5, B7. The improvement of 1% is pretty standard, and which is pretty nice, because this means that the filtering mechanism actually works well. Finally, they also show really good robustness results on ImageNet because of training on a lot of different data augmentations and model noises and a lot of unlabeled data in addition to labeled data. You would expect the resulting classifier to actually be good on adversarial robustness benchmarks, which happens to be the case. So they actually beat the state-of-the-art adversarial robustness benchmarks on ImageNet A, which is the corrupted version of ImageNet, where usual classifiers fail over there. And their model actually gets 83.1%, 83.7% top one, which is unprecedented. And they also do really well on ImageNet C and P, where they get very competitive, very good numbers on the top one accuracy over there, 77.8% and 86%, which is significantly better than the models that did not use this noisy student process. So here is like examples where the model that they train on these harder versions of ImageNet ended up making the right predictions, which is in black, while the baseline models ended up making the wrong predictions. So the baseline models are focusing on aspects like the wheel of the car, when there's actually a racing car, or like, for instance, they're actually looking at, so the model is able to capture the basketball in the photo on the bottom row, where there's a man holding a basketball, whereas the baseline models are not able to do that. So that shows this model is very fine-grained in terms of its recognition abilities. And here are bigger examples. There's a dragonfly on the right, but the baseline models are fooled in thinking it's a bullfrog. And similarly, parking meter versus vacuum, swing versus mosquito net. So this model is actually very good at the details. And they also have ablations for how much the noise matters in this process, and it seems to matter significantly enough. when you use all the different kinds of noises like dropout, stochastic depth, and data augmentation, you get the best possible numbers. So in summary, we looked at semi-supervised learning, and it's a practically important problem in the industry for two different scenarios. One is when you have a lot of labeled data and a lot more unlabeled data, like for instance, ImageNet and JFD, and you're trying to improve the performance of ImageNet. The other is when you have very little labeled data and you have plenty of unlabeled data, which is usually the case in medicine or finance or something like that. So the promise of semi-supervised learning has always existed for the second scenario, but there have been very good results in the last few months or like the last year or so in both these scenarios, which is the noisy student model really helping in the scenario where you have a lot of labeled data, but you have a lot more unlabeled data. But then unsupervised data augmentation or MixMatch is really very good at the low data regime where you have unlabeled data but very little labeled data and you're able to do really well. So this means that when you have a scenario where you're using unlabeled data to improve the performance of supervised learning systems, self-supervised learning is not necessarily the only option. Semi-supervised learning is as lucrative or probably even better because of its ability to improve the performance even in the high data regimes and make it possible for building ImageNet classifiers that have had unprecedented top-1 accuracies, like noisy student. That's it for the lecture. Thank you very much.
All right, so let's get started. Welcome back to, is it lecture 9? I'm actually not sure. Of deep unsupervised learning. Lecture something. And so we will have a two-part lectures today. The first part, we will look at something called unsupervised distribution alignment. It also goes by a lot of other names. And then the second part would be a guest lecture by Professor Alyosha to talk about some of, I guess, the works from his lab. So any logistics questions before we dive into your lecture? Milestone of the project? Can we have late dates for milestones?
No late dates for the milestones. Only for homework.
All right, there you go.
Can we have more credit for the project?
More what?
More Amazon credit for.
Yeah, we'll publish more credits for the project later in the year tomorrow. For the final project, everybody will get an extra $500 in credit, I think.
Oh.
So it should be pretty good. Amazon will be very generous. Some of the thinking part is that they're mostly excited about is working on the compression challenge.
Which no one is working on. All right, so let's get started. So in this lecture, we will look at unsupervised distribution alignment. So what does that even mean? So let's remove the part unsupervised. Let's just first look at a distribution alignment problem. So a lot of problems in image-to-image translation take this form. So let's say I want to go from semantic mask to RGB images. Then this is a distribution alignment problem because we can think of us having a distribution over mask here. And then we also have a distribution of like just regular images here. And then they would like co-occur with certain joint probability distribution. All right, it's mostly for one image, there's only one correct semantic mask, but for one mask, there could be many corresponding images. And the goal would be like, how can you align these two in such a way that when I give you an image on the right, you can generate the mask, or the other way, if you want to generate more training data. And then the more image problems that takes this form, let's say I want to know an image what does it look like in the daytime and what does it look like in nighttime. And then again, we can think of it as having a distribution of images of daytime and then also a distribution of images in nighttime. And then you want to align them in certain way. So you would say, why is this helpful? Like one way that this could be helpful is, say, if we want to train autonomous vehicles to drive safely at night, but then it's harder to collect training data at night. So is there a way for us to collect corresponding images during daytime and then find a way to find their nighttime counterpart? That would be useful if we can do this. And then there are a lot of other problems also fall under this formulation, like black and white images to color images. And for basically everything that we have seen, they are relatively tractable because like I can totally just take a color image and then convert it into black and white. And that gives me a lot of pairs that I can train on. And similarly to the semantic mask and street view RGB images, as well as daytime and nighttime. For a lot of those, you can actually find natural pairs. So these are some of the problems, distribution alignment problems in image space. And this kind of distribution alignment problems also happen in the text analog of that. And the most straightforward example is really just machine translation. How do you translate a sentence or a paragraph from one language to another? That, again, you can think of as a distribution alignment problem. You can think of there's a distribution of English text, and then there's a distribution of Chinese text. And then the question here is how do you align these two things together? So when this kind of distribution alignment problem, when it's supervised, then they are relatively easy. So when in the case of from an image goes to semantic mask, it's basically just semantic segmentation problem. When it's like other image-to-image translation, there's this text-to-text work that's done here at Berkeley. And then for text-to-text domain alignment, when you have the supervised pairs, it's just machine translation. And when you want to go from image to text, again, when you have supervised pairs, they are just like captioning task and other things. So in the end of it, it really just boils down to fitting a certain conditional distribution. Like you give it image B, what is the correct mask, A. And you have this luxuries when you have kind of A and B pairs that co-occur in the real world, either through your annotation effort or by taking an image at daytime and then take the same image at nighttime. As long as you can gather this kind of pairs, it's somewhat trivial, at least from a formulation perspective. It's really just fitting a conditional distribution. And we have talked about all sorts of ways to fit distributions in this class, GAN, autoregressive model, flow, whatever. But the question becomes interesting if this kind of pair of data, what if they are expensive to obtain, or they just don't exist? Then we are basically going out of the range of this supervised distribution alignment problem. Like you have one distribution, you have another, but you don't have any pair of data. Then like, can you still do this or even do it at all? So I'm taking some examples from a paper called CycleGAN. Like, what if you want to turn a painting into a photograph, or turn a photograph into a painting? The second one might be more tractable because like you could possibly say, I take a picture and then I hire someone to paint it for me. But if I want to do it in a very specific style by a specific artist, then you really couldn't do that. So in a sense, the natural pairs don't even exist in the real world. Similarly, like if you want to, for whatever reason, if you want to turn a zebra into a horse or turn a horse into a zebra, then it would be very difficult to force a zebra and a horse to take up exactly the same pose and take a picture of them having the exact correspondence. So these are the kind of pair of data that would not exist in the real world. And there are a lot of other applications. So let's think back to machine translations. So if I want to translate between Chinese and English, or English and Germany, that's relatively easy because there are large demand of those language users, and it makes it economical to annotate a lot of data of basically supervised language sentences pairs. But then like it's not economical to do it for the other probably hundreds of languages that exist in the world. It just doesn't make sense to annotate that much data. And if we can make this kind of distribution alignment to work without any supervision, then it could be used as a lot more, it can be used as a way to augment labeled examples in a kind of semi-supervised way. And it can be also used to do style transfer, like some of the things that we have seen that basically had no ground truth in the real world. Yes?
Economical in terms of paying the annotators?
Yeah.
And for the other languages, do they want to get paid more?
Well, it's just, okay, so if I have a good translation model between two languages, then the value of that model is kind of proportional to the usage that you can get from it. Let's say to train any pair of languages, you need the same amount of investment. Let's call it $50 million, probably on the lower side. Then, like, if I throw in this $50 million for between Chinese and English, you probably get a ton of usage, and you get ads or like what other revenue. But then I have like English to like whatever language that probably only 100,000 people speak. Then you get drastically less usage of that model. That means for the same investment, you get a lot less out of it. So it's not that they are more expensive to label, it's just like their value doesn't make it justified. So let's look at this problem again. So it would be, of course, it would be a nice thing to be able to achieve, to give me two distributions and then find a way to align them. But is this even a feasible problem? Right? So if we look at the problem statement, we are basically told to do two things. One thing is, we have distributions A, we have two random variables A and B, two distributions, and then we get access to the samples from them. Like we get a bunch of samples in one domain, we also get a bunch of samples from the other domain. So that's all great. But what we crucially don't have is we don't have any samples from the pairs. Yet we need to estimate how they are related to each other. So this problem from a high level seems pretty hopeless because you are really given too little information to tackle it. So what we would look at next are kind of certain, so basically the crucial problem now is like, where do we even get any training data? Like if I don't have any supervised pairs, like what do I even train the model on? So the way that people have been doing this is they try to rely on certain invariants that are true for kind of any pairs of distributions. And then somehow you could get some meaningful learning signal out of it. So the first kind of invariance that we can rely on is something called marginal matching. So there's some math here, but then the brief idea is really, like if I want to translate one distribution from one distribution to another, after the translations, the distributions should still look like each other. And more precisely, what it means is that there is some fundamentally unknown coupling. There's some fundamentally unknown relationship between these two random variables A and B that we are trying to approximate, but we don't have access to them. So let's call that our approximation Q. So given B, like what A is most likely, well, this is the other. This should be. So basically, we were trying to learn two mappings or two conditional distributions. And when you specify this kind of conditional distribution Q of A given B, you implicitly induce a marginal distribution. So when I specify Q of B given A, I'm implicitly specifying a marginal distribution on B. And the way that you compute it is, if I sample A for my ground truth distribution of A, and then you essentially average out this conditional distribution, that would be the marginal distribution of B. And ideally, I want my Q to be close to the ground truth conditional distribution P of B given A. And that means if I sample a lot of A, and then I map it through my conditional distribution, the outcome of that should map back to the original ground truth distribution. And similarly, I can do that for A. So I sample from B, and then I would, from this B samples, I would calculate my approximate conditional distribution. And after those transformations, they should be the same as original marginal distribution as A. And oftentimes in literature, this conditional distribution is just a deterministic mapping. So I would say, give me any sample from A, I would map it to its corresponding sample in domain B. So far, so good? Yes.
So assuming Q is like some neural network,
Yeah.
Even though it's doing something that's like dependent on A or like using some of the A information,
Yeah.
it seems like when we're training this, we're just going to be minimizing some loss between PB, like what we actually have, and the result of Q. So at no point is A impacting how we train like Q for B.
So the question is, basically we have stated the question to be, in the end, we are trying to match this marginal of B, approximate B, to the ground truth B, which we have access to. But in no point you're saying the neural net Q needs to look at A, essentially. So that is a true statement. So if my Q is so powerful that it could just represent the whole marginal distribution of B. So let's call, if we have Q of B given A, that is equal to Q of B for all A and B pair, then your statement would be true. Basically, you can just like approximate the marginal distribution without even doing any meaningful work. So that's why, like in practice, people would have a fairly restrictive mapping.
Okay.
So like that's why, like in most of the works that we would look at, like it usually takes the form of a deterministic mapping. So when Q of B given A is deterministic, then like you don't get to represent the whole marginal distribution unless P of B itself is only a point mass. But that is a correct observation. But like you suggested, like I mean, this is a very weak learning signal. Like if you don't construct your model in the right way, like you could extract nothing from it. So let's see some examples of like how does this in an ideal case work at all, right? So let's say I have two distributions, A and B, and they are very simple categorical distributions that only have three possible values, A1, A2, A3. I'm just going to draw some frequency here. Right, so and then I'm going to do the same thing for B. So this is probability mass function. Right, so based on, let's say we have a deterministic mapping. That means like each of the A has to map to some B, and each of the B has to map to some A. Then like based on the marginal matching, like this can seemingly give us a way to recover the ground truth correspondence. Let's say the ground truth correspondence is between A2 and B1, and A3 and B2, and A1 and B3, right? So I would argue this would be the only correspondence that satisfied the marginal matching constraint. Why is that the case?
Is this always going to be bijection?
Well, it could be not a bijection, but then like it might not fulfill the properties unless some of the values have like no probability mass. Then like you can do whatever. Right. So I argue this is the only way that you could make the marginal matching work? The reason is that because each value has a distinct frequency here. So if you match it in the wrong way, the marginal distribution of the induced mapping would no longer be matching the original one. But there was still a lot of ambiguity, right? So if we imagine a distribution that's like the most difficult one, let's say I have a uniform distributions over 2 random variables, then this is kind of hopeless because all kind of mapping could work. So let's first look at the A to B mapping. So A1 can map to B1, A2 map to B2, but then it's also possible that A1 can be mapped to B2, A2 map to B1, and would still be fine from a marginal matching perspective. But then the problem is, then that means this thing is ambiguous. And this is not just, oops, sorry. I meant to draw it the other way. So there are 2 sets of mappings that we need to learn here. One is GAB, which is mapping from A to B. And then another set of things is, another set of things that we need to learn is GBA. And basically, you would need to learn the product of these 2 different possibilities. B1 to A1, B2 to A2, B. So how many totally possible solutions are there to this problem if we just use marginal matching?
2 by 2.
Yeah, so basically each direction there are 2 possibilities, and then if you multiply them together, there are 4 possible solutions in this problem, and they are basically totally ambiguous. So this is one of the things that we are seeing here is you can have your objective function that induce a really large solution set. Really, in this case, is almost all of the solution set. And then people realize this can potentially be a problem. So they introduce another technique to try to at least restrict the solution set a little bit. So this thing is oftentimes referred to as cycle consistency, but it has also taken a lot of other names in literature called dual learning, back translations. And really the core idea is that if I take my, so basically the core idea is that my approximate mapping should be similar to the ground truth mapping. And if those mappings are deterministic, then what that means is that if I step through my mapping, I should get back my original sample. So if we think about the case of B of AB given of A, would be this would map A to its correspondence in B. And then if you apply that again from the other direction, B to A mapping, you should get back A. And this should hold true in both directions. So this gives you another invariance. So if you say that the relationship between these 2 distributions are indeed deterministic, then I would say these things should hold true for all possible pairs. And if we step back to the example that we just looked at, so if we impose cycle consistency, what would be the number of possible solutions now?
2.
Why is that no longer 4?
Otherwise, you cannot invert it.
Yeah, so we can see that in this case, the original total solution set is 4. But after you impose this cycle consistency constraint, you can reduce the solution set that exists. Some of the mapping are no longer valid. So let's say if I pick this and then pick this would be no longer valid because an A1 would get translated into B1, And then B1, according to this, would get translated into BA2. So this is GAB. This is GBA. And this no longer satisfies the cycle consistency constraint. So that means like I can use this constraint to reduce the possible solution set in my search. But still, like we can see that it's still fundamentally underdefined. Like we are still left with 2 possible mappings, and we are not sure which one is correct. But it at least exponentially shrinks the space that is possible. So far we have seen the 2 core invariances that people have used. And these are invariants that are true for all alignment problems. And then we can use them as learning signals. And again, like obviously, like we just look at, like even in a extremely low dimension, basically categorical examples, like it's still not going to work. So there are definitely problems that this cannot solve. But then in practice, like people can find problems that this kind of search is amenable to. And then you can oftentimes inject additional biases in your system by selecting the right architectures, loss functions, and etc. And you can actually get to a certain level of success with this. Yeah.
Can you explain more about the previous slide? The expectation, the previous one. Yeah, the expectation.
So this one basically says, for an arbitrary data point it's just a generalized version of the cycle consistency thing. So for any of the data point A, if I draw samples from my approximate conditional distribution, and then I translate that B back to A using my approximate ones, the distribution that it induces should be similar to if you do it with the real world one. What we're saying here is just that, like, when in the case of when we say we know the P and the Q are both deterministics, then it reduces to the deterministic mapping example. But it could exist in a more general form. So probably the best known example that uses those learning signals are CycleGAN. So CycleGAN's laws essentially consist of 2 parts. One part is this marginal matching. So meaning after I translate my data from one domain to another, the marginal of them still match with each other. And you can kind of see it here. So essentially, my generator no longer takes a mapping from Z to X. Instead, this thing is trying to translate from X to Y. And I want to do it in such a way that it looks like my target image. So this is just a standard GAN training loss where you're trying to say, my mapping from X to Y, it should look like just like Y. So that's fairly straightforward. And so essentially, instead of looking at frequency, you use a GAN to help you do the marginal matching. And the second dimension of this is you can achieve cycle consistency by an L1 loss. So essentially what if we unpack this objective function is, you sample for data in one of your domain, probably your source domain, and then you map it through a cycle, then it should look like itself in an L1 sense. So this is, I think, what they call forward cycle consistency, because it's going from X to Y to X. And then they also have a backward one where you essentially kind of think of it as a sample from all your labels, and then you map it through this thing again, Y through X through Y should be similar to itself in an L1 sense. So that's the loss function. And then you essentially would combine these 2 things together and then train it. I think in practice they use a least square GAN instead of the original GAN objective, but probably it doesn't make too much of a difference. And so they reported a couple numerical results. And the first results that they look at is, so in the case of going from photo to semantic mask, you can actually calculate the accuracy. So we can get a quantifiable notion of how well the method is doing. So the method that we just introduced is called CycleGAN, and it's basically unsupervised. So you give it a bunch of street scenes images and then a bunch of semantic masks, and then you hope them that they somehow align each other. And what this shows that they actually do pretty well. So a pick-to-pick is a fully supervised model. So the last row means you actually get pairs of image and their corresponding label. So the last row should be read as basically an upper bound on the performance. And then the CycleGAN, by using no labels at all, it can actually do pretty respectfully. So like you can roughly say that 60% of the pixels are labeled correctly with the right class, with actually no information on how they should be related to each other.
Do you have to put the images in pairs a priori, or?
No, so there's no pairs. So you train the whole system with just a bunch of unordered images and then a bunch of unordered masks, and then it's learning to align them. Yes.
Does the performance of the CycleGAN tell us anything? Like, does it get better accuracy on like, I don't know if the cityscape does it do well on cars and worse on street signs? Like,
Good question. I don't think they have that level of analysis, but I think that would be interesting to see. Like, what are the kind of things that are easier for it to align? What are the things that are not, like, a more trickier? Yeah.
I feel like there's a lot of inductive bias in like going from one picture to another.
Yeah.
Is there like any experiments done between like data that's not as structured?
Yeah. So the question is, there was a lot of inductive bias going from one image to another using a convnet, and then also using a certain discriminator that operates on a patch basis. So you kind of like do a kind of domain alignment per patch. Like, so you can think of it as having, there's really a lot of training signal that is not captured by the loss function at all. So unfortunately, we don't know the answer to that. So I guess what I know for sure is like if you just scramble the image, just permute the dimensions in your image tensor, then I'm pretty sure it would do poorly. But then like, does that mean like this is not useful? Probably not, but it still means that we don't fully understand what are the inductive biases that are helping us. But that's a good question, yes?
I think one is like, for images at least, it works well if the shapes in the two different domains like match relatively. Like they had one good example, like horse to zebra, like the shapes of those animals are pretty much the same, it's just the color that you're changing.
Mm-hmm.
But it's hard to do like, I don't know, like automobile to like a pickup truck or like a giant truck.
Right, so I guess, so the comment is around like a lot of these translation problems like operate in a very local manner. Like you're kind of like saying, I just need to change my local pixels. Like when you go from zebra to horse, like you're just kind of changing a local texture as opposed to something that is global, which is presumably much harder. I think that's likely the case.
Could you explain what the feature loss of GAN based on?
I have no idea. You can ask Alyosha, who will be here soon.
How does this result compare with supervised learning if you match?
So I think this is a long way from supervised learning. So I believe supervised learning, like this thing should, like I don't know, but I imagine this to be at least 95% plus. But again, like this is not a correct comparison. I think the correct comparison is to compare CycleGAN with pix-to-pix because they use similar architecture, except one is supervised, the other is unsupervised. Oops. All right, so they have some ablations in terms of loss function, although not in terms of architecture. The ablations basically tell you what we sort of expect that like for one, like if you GAN alone, if you just do GAN alone, this means you just do marginal matching. So which is actually not bad already. And then you can see that if you add cycle consistency in there, it helps you. And there's something that's really puzzling. Like I'm really confused by what is happening here. It just kills everything. I have no idea what is happening there. So I don't know. And what's also interesting is that it doesn't always help. So what we are looking at going from photos to labels, and then they have another experiment that is going from labels to photos. So this is a much higher entropy mapping, whereas they still use just deterministic mapping. So you can imagine there might be something that is playing with that in here that I guess we don't fully understand. What's interesting here, though, is the evaluation metric is pretty interesting. So remember, here we are evaluating it from label to photos. So basically, it's give you a semantic mask, how well you can generate a scene. But then how do you even evaluate that? So they actually have a pretty clever way of evaluating that. So what they would do is they would run another pre-trained semantic segmentation network, fully convolutional network. They would run it on the generated image, and then they use that to quantify the results. So that is a pretty interesting trick to evaluate this mapping.
Just like the inception score?
Kind of like the inception score, except like in this case, like it's kind of like inception score. But I think it's better than inception score in this restricted domain. These are some of the other success cases where you translate from, I guess, a schematic annotation of a facade to a facade, going from edges to shoe, going from shoes to edges. Most of them make sense. They apply this to a wide variety of different problems where it's just impossible to get label pair. It's just like, I guess summer Yosemite and winter Yosemite you can get pairs, although not exactly the same. And translating apples to oranges. Just like we said, like this is, it's not, like since it's not supervised and it's not fully unique, they have their set of failures. And in this one, what the authors explain in the paper is that, like, I mean, when you train on, or maybe it's a success, I don't know. When you train on horses in ImageNet dataset, they have not seen a human riding on it, and as such, like, you would just classify all similar texture to be horses, and then you just translate that. So, like this I guess goes back to one of the questions that someone mentioned. That's like, what are the failure cases? So, like, I think this is one good example of like what it fails on. Like, I think this is a good example of what the model is doing is trying to find like yellowish pattern, and then change that yellowish pattern to stripes. So that's apparently what the model is doing. So that's that for CycleGAN. So essentially, it's pretty surprising that it can work on certain domains, and when it works, I think it's fairly reasonable. So the next thing that we would look at is we'll look at improving CycleGAN in certain dimensions. So the crucial dimension that we would look at here is that, remember when we talk about the CycleGAN has this deterministic mapping. So you give you an image X, you translate it into domain Y, but this translation is deterministic. But that is fundamentally not correct, at least for a lot of the alignment problems that we care about. So let's say if I want to go from mask to image, semantic mask to image, like there's a lot of different ways to satisfy the same semantic mask. There are a lot of different ways to generate that image. Like semantic mask only tells you there's a car here, but what does the car look like? What's inside the car? What color it is? Like it specifies none of those. So basically there's this high entropy mapping going from semantic mask to image, and that is apparently not deterministic. So you can say, oh, one straightforward way to extend CycleGAN is to say CycleGAN is essentially this, right? So you take in an image A, and then you're trying to map it to image B. So one straightforward way to extend that would be to make this mapping take in an additional noise source, just like in a typical GAN. So you could take in an image A, and then you can also take in a noise source that probably describe like what does the car look like, what is the color other than the contour, everything other than the contour. And then from that noise source, you can map to some image B. And then if you sample different Z's, hopefully you get different cars. Does the motivation make sense? So that's all good. So, and in fact, like this has been done concurrent to CycleGAN. There's another paper called DualGAN, where this is essentially the architecture. The mapping would take in both an image from source domain as well as a random noise source. However, this is not enough to just change your architecture, because even if you change your architecture, the noise are doomed to be ignored. And to see that, the reason is essentially our loss function, the L1 cycle consistency loss, tell it to do the following. So if I map my A with certain Z, this produces like some kind of B for me. And then if I map my B with another Z prime, I should get back to A. And we can see that in this whole mapping, the choice of Z and Z prime are essentially ignored. So you can choose different Z or Z prime. You still need to satisfy this mapping. So what that means is that the noise source is necessarily ignored when you impose a cycle consistency loss and when you optimize it to its fixed point. So that's not good. And then there was this augmented CycleGAN paper that proposed a way to solve it. So you would augment the noise to your architecture, but you will also learn. So instead of only learning the mapping from A to B and B to A, you will learn an encoder of each of the noise source, not dissimilar to how an encoder is used in a variational method. And it's actually pretty interesting. So the way that you would go is I have some ground truth image A, and I have, then what I'm going to say is that my ground truth image A would come from a corresponding B and its corresponding noise source, ZA. And then I would have this blue arrow, which is a network that infer what ZA it is. So basically, I'm trying to infer what Z produced my A. And I'm also going to infer what B produced my A. So instead of only inferring what is my corresponding B, I infer that as well as what is the noise source that produced me. Now, with both the noise source and the corresponding B, I can use that to map it to an A prime using this color, which is the mapping coming back from B to A. And in the end, I can say that A and A prime should be similar in L1 loss sense. So now it's okay, because I'm choosing a specific Z for each particular data point. So if we think about it from an information theoretic sense, whatever information that is not captured in B, you push it into Z. That allows you to perfectly reconstruct the original image, as well as maintaining the ability to have diversity of mappings, because a different A could come from different Z's. Yes?
How do you prevent the model from pushing everything into Z?
So the question is, how do you prevent the model from putting everything into Z? So you could, but it might fail the marginal matching criteria.
Well, the marginal matching just says you need to output like a distribution of B that looks good, right?
Right. So I guess the statement is like the A and B relationship could become decoupled. Like from A, I would just map to an arbitrary B that actually has no correspondence with A from the beginning. But then, like, remember, that is always the problem. like even with the original CycleGAN, you could still produce an arbitrary mapping that is consistent, but it's not the ground truth mapping. So this, like, I guess what I'm saying is this doesn't make it worse. Yeah.
Could you do like maybe where you have the distributions match after a cycle, like distribution induced by having a Z, like rather than having like an L1 loss?
Sorry, can you say that again?
So like you map like A and Z to B, and you have another Z that goes back to A, and the distribution is induced by that, like, because that's a stochastic mapping. At that match the original distribution for A.
So are you saying like basically you can play this multiple steps, and then like the evolution of them should still match the original marginal distribution?
No, I'm not fully sure.
You're saying like take one loop and then the result of that becomes your like stochastic noise.
Yeah, more like that.
Yeah. I mean, yeah, that's it's like if you're to stack them.
I guess, yeah.
Yeah, so there are many ways that you can play with this. Yeah.
Which I'm still a little confused, because like to me this looks like A to A prime just looks like an autoencoder going through Z, and then you also have like something else that goes A to B, right? And you have like whatever, some GAN loss on B.
Yeah, you will have GAN loss on B, and then you would, I think you also have GAN loss on Z, which like Z you restrict it to be, the marginal of that you restrict it to be some Gaussian or something. So in a sense, you cannot put infinite information in there. So both of them are in a sense information regularized. Yeah, good go ahead.
Okay, that's just like a VAE, right? Just like
It's really more like an adversarial autoencoder, which we didn't cover in the lecture. So it's kind of like a VAE, but instead of like a KL loss, you use a GAN loss.
Okay.
So it is more, it is, but like it is very much like a latent code model that is trained with a GAN.
Like, I just don't see how, like, why the model wouldn't just collapse to that.
It could. I'm not saying it wouldn't. Like that applies to everything that we'll go over today. There are holes in all of them.
Well, maybe it's because VAEs just don't work as well as GANs. So
Oh, you mean why they don't use a VAE?
kind of like good reconstruction loss on A prime, just doing 100% VAE is not going to get back with a loss.
I think it's probably the mapping from A to B that it wouldn't do well. Like it wouldn't do it in like a visually appealing way. Otherwise, I think for Z, they could actually use a VAE type of loss. But it would not be a VAE because there's still this thing that's in the middle.
On that point, but doesn't the VAE start generating stuff like way before the GAN does? So then in like the life cycle of training this thing, it would be able to like take the VAE path while the GAN path is still underdeveloped, and it seems like at that point it would like shift into Z. Because I understand at the end of it, yes, the VAE path will be worse than the GAN path. But it seems like from the homework that we did, the GAN path takes so long that I was prepared to do 47 hours of training compared to like one.
Actually, comparing to the data sets, like the VAE homework was on Chen and GAN from C.
Yeah, it's not that fair comparison. I would say though, like if your data set is small, like GAN training is usually pretty fast as well. Yeah. Anyways, but that's off topic. So just like operationally, what does that mean if we go through like one cycle of that, well, cycle consistency loss? So we get some image from from a source domain. And then we would randomly sample a Z for my mapping to B. Because remember that the mapping from A to B is also stochastic. So B could take up a lot of different forms. And then I'm going to generate a noise source that dictate what it is. So this is what I'm going to sample. And then there will be a set of mappings that I go through. So the mapping from A to B, now it takes A and a noise source for B. That gives me B. And then from this B and A, I can try to guess what was the Z that has generated my original A. So that is my encoder to guess Z of A. And then finally, I would plug in the B that I generated and the Z that I generated. And from these two, I get back this A prime, which supposedly should be close to my original sample. So that's all good. Like it's fairly easy to implement, like just a small surgery on CycleGAN. How does it do? So the first thing that you would want to run is essentially you would want to first give Z as the additional input to the mapping, which they call stochastic CycleGAN, I guess. So that is without changing the loss function, like without introducing the encoder, is what this column that we are looking at. And then the test here is we sample an edge map for my ground truth data here. And then I would feed it through my CycleGAN, but with different Z terms. So this is, imagine this is coming from Z1, Z2, Z3, Z4. So this is surprising, right? Because we went through this argument of like how just changing CycleGAN to make you to take in Z wouldn't actually make use of Z, like it would just ignore it. But what we are seeing here is actually different, right? So you give it an edge mask, and it actually generates diverse samples for you. So that's interesting. Like if we look at, like say this shoe, like apparently they're all different colors. And even though we do the augmented one, like using the new loss function and the encoder, I would say they look probably about the same kind of diversity. But then it's kind of interesting, like why does CycleGAN work? Especially like this is highly contrasting with the analysis that we just went through. So especially if I take a black shoe and then map it to its semantic mask and then map it back, then if I get a white shoe, which is according to here is something that could happen. If I get a white shoe back, I'm going to incur huge L1 loss because black and white are just two ends of the spectrum in your color space. So that is somewhat puzzling. Like what is this actually doing? Like if it can generate these diverse samples, then that means it's not optimizing its CycleGAN loss well. But it is optimizing its CycleGAN loss well. So the very interesting thing here is that CycleGAN, when you go from a high dimension, like a high entropy mapping, like RGB images, to a low entropy one, like a semantic mask, it can actually hide information in some kind of high frequency pattern. So this is what we are seeing here. So like going back to the black shoe example, like when you map from a black shoe to its edge pattern, like it would give you like a seemingly plausible edge patterns, and then add some high frequency noise to it that denote that this is coming from a black shoes. And then it can look at the rough shape of that pattern, and then it also reads the high frequency noise that's encoded in there to say, oh, this should be black. And that's how it manages to still do the cycle consistency, right? So I consistently get the same color back by hiding imperceptible information in sort of my mask on my edge. And that's pretty interesting. The way that you can show that it's doing that is by essentially constructing an experiment where you, so this is called domain A, this is domain B. You get the B out, and then you try to sample different Z that, you try to fix that B, and then you try to sample different Zs. So if this is coming from a CycleGAN loss, then you will see that the mask itself, even though seemingly it doesn't encode color information, it's implicitly encoding color information. So if I take this mask that's come from my model, I would have color information hidden in it in such a way that when I sample different Zs, you always get the same output. And that's how it's able to still satisfy the cycle consistency constraint. And then if you do the augmented CycleGAN loss, what you will see is that the mask look basically the same, but there are seemingly less information in there. So when you sample different random noise source Z, you actually get different color of shoes back.
Peter, do you know how large Z is? It seems like all it encodes is color. So is it only like a
I don't remember. That's good to check. But I guess as we have discussed, like if Z is very powerful, then potentially it can encode too much. So I think there would be a balance there. And this is kind of doing the cycle walk. This is somewhat interesting, somewhat similar to what we had discussed. So map it from A to B, and then B to A to B, while I cycle through different noise source. And then if you do this kind of random walk in an augmented CycleGAN, you can see that even though the mask stays relatively the same, the overall appearances, some of the other color texture does change over time. Whereas if you train it with the original CycleGAN laws, you would just get the same pairs repeated again and again. That's a somewhat interesting, in my opinion, relatively simple and elegant extension to CycleGAN that help you to deal with stochastic mappings. Any questions on that before we move on? So the next set of questions are, can we do better? So far we have covered two learning principles. One is marginal matching, and then the other is cycle consistency. And I guess it's a good question that whether those are all of the invariances that we can rely on, or are there additional learning signals that we can derive from it? It's a good open problem. And if we step back and think about this whole problem, it's really aligning two distributions without knowing what's inside is just really difficult. If we think about the categorical distribution that has even probabilities, like it's just impossible to align them because we treat them as pure black box, like all values are the same as each other. So one idea that we can move forward from this point is we can look inside the random variable. We can say this image is not just a high dimensional random variable to me. Like I can actually look inside and see what's in there, and then maybe use that to help us. And for this kind of high dimensional A and B, like they typically have certain structures in them that could be leveraged. And as people have pointed out, like when you use a ConvNet and patch-based discriminator in a CycleGAN, you're kind of implicitly employing some of this inductive bias already. But I think there are cases where we can push this even further. So the best example that I could find is in NLP for that. So let's say domain A is all English sentences, and domain B are all French sentences. Then we can imagine that like I can get a random sentence from all English sentences and a random sentence from all French sentences. They might have the same empirical frequency, but they might be totally semantically unrelated, which is likely to happen. And cycle consistency wouldn't also rule out that either. This is just basically going back to the problems of when you have distributions that have uniform densities, nothing could help. But what we do know is that each sentence is made up of words. And it's very unlikely that in those two totally semantically unrelated sentences, they would have words that have same kind of statistics. So I'm using the term statistics loosely here. I'm going to say more about like what we can do with this. So basically, what the exercise that we have gone through is, instead of thinking of it as distribution alignment between sentences in different languages, if we are allowed to look inside, like what's within each random variable, and look at their subcomponents, and do some inference on the subcomponents, that can help us circumvent the problem of not enough learning signal. So in the case of NLP, the subcomponents are the words, and the larger, higher dimensional random variables are sentences or paragraphs. And so that's interesting. So right now, what we can do is we can first of all align the words. Like we can think of ways that you can do distribution alignment on words. And even more, we can think of, we can make use of how different words occur together. So let's say the word I is most likely to be followed by M, and because these two things co-occur most frequently in within this large random variable a sentence. So what is the thing that we can make use of this kind of co-occurrence statistics of subcomponents? Well, we have learned one of them, word2vec, in 2 lectures ago, probably. So just a recap on CycleGAN word2vec. It's really simple. So basically, all it's trying to do is trying to say, given one word, the word in a sentence, I'm going to say that other words in this sentence is more likely to occur than every other things in my corpus. And in practice, you wouldn't sum over all of your dictionary. You would do some negative sampling to optimize this. But essentially, the end result is certain vector that describe if 2 vectors are close together in that vector space, then they are more likely to occur in a sentence. And if you train a very, very large model on a lot of text data, then it captures how different words are likely to occur together. So that's CycleGAN. And what's really interesting is that this kind of word2vec method exhibits really interesting vector calculus. So this is, again, a recap slide. What we can look at is that if we look at the direction from a country to its capital, the vector is actually relatively similar across a lot of these different pairs. And we might be able to ask, like, so based on this kind of vector, if the vector calculus makes sense, then does it mean that we can say the vector representation of those words are distributed in a certain manner? And more importantly, if similar vector calculus holds true for all languages, meaning I train a word embedding for English, let's say on the left, and I also train a word embedding for Italian, if they exhibit the same vector calculus, meaning all different embeddings in them are placed together in such a way that you could do the kind of country to capital translation, then that's a really strong inductive bias for us. And if that holds true, then we can possibly align words by just like uncovering some kind of affine or linear transformation that align these two things together. So very surprisingly, it's actually true. So for the word2vec that we use, let's say in fast text, if you train it on one language, if you train on multiple languages, and then these embedding space, they are only a rotation away. So you're going to learn a rotation matrix that rotate another language into your space. And then the results would be, well, this is graphics that I grabbed from a Facebook blog post that illustrated really well. So you basically get this embedding space that exhibit similar relative structure. And then, so what you can do, but the absolute location is undefined. So what you can do is you can just learn a way to align them together. And then after the rotation, one point in the embedding space would be very likely to exhibit the same word, but in different languages. So this totally blew my mind that this could work. But yes.
So do you have some like labeled like pairs of words, and then you use that to learn the?
Yeah. So initially, what the citations here are, you can basically use a small dictionary, say a language-to-language dictionary. You can use a small dictionary to learn the alignment. So it's still supervised. But the search space is much smaller. Like instead of going from each word, map through a neural net, and then map to another word, you would be like, every word is already represented by some embedding. Now I'm only learning the rotation that is used across all embeddings. But then, like, so basically a couple data points is enough to specify that. Yes? I don't know. Probably 2,000, I would guess. Like, I mean, totally uneducated guess. I'm not an NLP person. It could be pretty big, yeah. So that's pretty interesting. So that's what happened up until like probably before 2017-ish is people can, like, you can align these two embeddings by, it's basically examples. Like I can just go to like French, English dictionary and then look up a couple words and then you use that to align these two embeddings. But that's really cool that you can do that.
Question?
Yes?
So why is that even scale is not a problem?
What?
If one of the embeddings were just scaled differently from the other one, then
Apparently they are scaled the same or less similar enough. And then there's this recent paper that proposed a way that you can, actually another thing that I forgot to mention is, actually this is it. So basically that's a supervised way to align this word embedding, right? So that's really interesting that you can just capture that by a simple rotation. Well, probably not simple, but a rotation. And what this work has done is to show that you can actually do that with really good performance in an unsupervised way. So now I have two embeddings, space, and then you are aligning them without any training signal. So the way that is done is actually basically just using the principle of marginal matching. So you would similarly apply, so basically your rotation, each possible rotation basically specify a mapping. And then you're going to say, after the mapping, my marginal distribution still match. And then they just train that with adversarial training. So like again, like a loss to make sure that the marginal is specified, the marginal is matched. And then after they do that, but one of the results of possibly due to gain training is usually not very robust and high precision. So after they do that, they have found a rotation that roughly aligned two distributions. And then after they have that, they would select some top pairs of high frequency words in those rough alignment. And then they would assume that they are actually ground truth alignment. And then you would use those as like actual pairs to solve for the exact rotation. And apparently this works really well. So that's some of the data that you get from, there's some additional tricks in terms of embedding nearest neighbor that I didn't go into. But that is the results that they have. And they're comparing that with cross-lingual supervision and without any supervision, which is their own method. And it's really surprisingly, they could get to competitive performance with using ground truth data of actual pairs. So there's, again, like this is not as complex as translating whole sentences. This is only translating words. But I still see this as very impressive that this can work at all and become very competitive with supervised methods. So then the next part of this is, again, another paper from Facebook, is now you can actually leverage all three of the core principles that we have covered so far. You can look at, so they use word level alignment, meaning they started from what we just looked at, the unsupervised level, the unsupervised word level alignment. So this is, you're not just looking at sentence level, you're looking inside sentence to subcomponent level statistics. And then they also use a monolingual language models to make sure what you translate actually looks like a real sentence, so that basically you can see that as marginal matching. And then they also have this thing called black translation, which is another variant of cycle consistency. So you translate it from English to French, and then French back to English, you should get back the same sentence. And this is a paper that essentially utilizes all these three methods. And then from there, I think they get state-of-the-art unsupervised machine translation results that are, I think 10, I don't remember the precise results, but that were widely beyond previous state-of-the-arts. And these are some of the ablation of showing how many training sentences they use in order to surpass this kind of system. So you can see that you would need probably somewhere between 500,000 data in order for it to surpass the flat line, which is the unsupervised machine translation results. So that's that for that method. And so again, like none of the kind of principles that we have talked about so far are bulletproof. But I think what's really interesting is you can seemingly extract training signal out of nowhere by just carefully considering the problems of what are the invariances that you can exploit. And especially in NLP, like really thinking about how, thinking about it not at a random variable level, but really look inside each random variable and what are some additional co-occurrence statistics that you can employ that could actually help you learn better. So that's that for this part of the lecture. Should we have pizza break?